So we're going to move into models, right? So time series models at least. So we're going to talk about models basics. And I see we only have, it's about at the 20. I know we're supposed to end at the 30. How are we feeling with time? Like, does anyone have to go like in 10 minutes? See some head shakes. Okay, so you guys cool if I just kind of extend it out a little bit longer than that? Okay, otherwise I'll just have it recorded, I guess, right? So you guys go through there. We'll go through at least the model basics, and then I want to at least talk about ARMA. I'll be upfront. I don't think you guys have to stress out too much about modeling for time series. It's not necessarily something that is expected of you, that you like every data scientist must know how to do these things in time series. Will it be helpful for you? 100%, right? Will it likely be asked in the interview? Yeah, give or take. Depends on the industry. But a good thing to ask is like, you know, people's like, oh, you know, what do you think of time series? Or if they say time series in like the thing, or if you're looking at like financial data where you know it's going to be really important to have time series, then digging deeper into this. But again, we could talk a whole like months about time series and stuff like this and modeling with that. So, you know, there's just the basics. And I think if you know the basics, you will do well enough in pretty much talking to anyone. And I say talking to anyone, that means interviews or just discussing, you know, a time series in general. And then if you want to know more, you can always ask more or learn a little bit more about this. Okay. I do not claim to be an expert in time series for sure. But these basic ones, so these are the really basic models. The white noise model, which white noise, you guys all know what white noise is, right? When I say white noise, like in general, like think of like, most TVs aren't doing this now, but like back like analog TVs, you turn on the TV and like you're not hooked up the cable. It's all like the white noise, right? Static, right? And like, think the Ring, right? Back a few years ago, like right before whoever comes out of like the TV, that's kind of what white noise. And basically white noise is just randomness, right? And so as you might guess, it is a stationary series because it's completely random, has nothing to do with time. Well, we can say, well, okay, we think this model is random. Hey, we can make randomness. That's a model. So some properties of a white noise model. We have a fixed constant mean, so it doesn't really change because it's random. There shouldn't really be too much of like a change in the like the trend upward or downward, right? It's random, so it should be fluctuating around 0 or something along that, or whatever value it has, a constant mean. Constant variance, again, random. There's not going to be any pattern in the variance, and no correlation over time. Again, pattern is pretty random. This is like the most interesting thing you can probably have other than like a straight line. Like, I'm sorry, the least interesting thing besides just a straight line, because like nothing's really going on. So, note that the Gaussian white noise model has a mean of 0 and a variance of 1, just like a Gaussian distribution, right? Like officially there's one Gaussian distribution. It's a mean of 0 and a standard deviation of 1. But of course we can expand it out. Okay. One quick thing before I go into the example, people might ask, like, why do I need to make a white noise model? Like, that seems kind of like, I don't know, dumb. Like why do I need to make this? And part of the reason is, like, so you can see, like, hey, can we compare this model with what we have right now? And does it seem random? Or if we're actually producing results. So we want to generate a white noise model and then pass it through different, basically different processes to see what happens when we have just random noise and stuff like this and what that looks like. Okay, so this can be really useful. So I'm going to actually create a series, right? So basically I'm going to create just something for us to work with. And then I'm going to create a normally distributed temperature. So note this date series right here, pd.date range, which I think is probably new for you guys. We can actually make a something that starts with, you know, a certain date. And then it'll actually, you can expand it out by number of days. So we can say basically, oh, we're going to have 100 days from the start of January 1st, 2015. Okay. We can then create a normally distributed temperatures. So we're going to have our average temperature is going to be 10, right? So the fluctuation is going to be around 10, and then the standard deviation is going to be 3. So we're not going to have huge wild fluctuations. We're going to have like standard deviation of 3. Okay. And then what we can do, we can take these two parts, which is our data series. Oh no, sorry, I'm going to split this up because this makes it a little bit easier for us to read. Data series, we got our data series, and just to kind of show you guys. Oh, date series, sorry. There we go. You can see, there we go. See, all those nice years, really easy. And then we can see right here, what we're gonna do, we're gonna do an np.random normal, normal meaning normal curve. We're gonna have the average temperature, the standard deviation for the temperature, and the number of days. So we're gonna have 100 different points, right? And just to make sure we can see this. can see, there we go. So right here, we basically have a bunch of points that go basically average around 10. So if I do dot mean, I'm gonna mess this up later. Sorry, I don't want to, I know what it's supposed to look like. That's why I don't want to run it again, because I have the same seed. But you can see here the average, 10, right? And if I do standard deviation, we should expect 3, about 3. So about what we expect. Okay, so cool. We got our dates, we got our white noise. What do we do now? Put them together. And there we go. So you can see here, we got our data, which is basically just the temp series right here. Those are the values. And there's say index. We're saying, hey, we have a series basically, and that series is going to be just the date, right? And you can see here, really nice. Look how nice it is when you have a time series. It just automatically says, oh, I know what this is. It's January, 2015 and stuff like that. Cool. All right, sound pretty good? Pretty easy to make this guy. Any questions at all about anything I did? I'm going through it pretty quickly, but I think it's pretty self-explanatory, right? I could be wrong. Maybe it's not self-explanatory, so. All right, so cool. We got our data. We made some random noise. Sweet. What's next? Random walk. So has anyone heard of random walk before? Sometimes you hear this in like conversation data science stuff. Oh, good. No one's heard about it before. Awesome. This is fun. So a random walk is like a drunk person. Pretty much what it is a random walk is that it's kind of, it's random. Like you think about this is completely random where literally there is no dependence on time, right? It just randomly picks a value every 2 time step, right? If I go to the next time step, it's just as likely to be like, some big value versus some very small value, okay? A random walk does depend on time, but it's still random. So the idea here, usually the comparison is like a drunk person walking around like in the bar or out on the street, is that they're at a certain point, but they're kind of like leaning back and forth because they're a little inebriated and they might take a step left and they might take a step right? But what direction they go, who knows, right? It's random. And so they'll maybe take a step right? And then maybe the next time they might go left or right 50% of the time, but let's say they go right again, right? And so their motion is going to be dependent on where they were previously. Does that make sense? Right? Because you're taking steps, you don't expect to be like at the same point that you started off with. So maybe it's better if I actually do a little annotation. So, oops, draw, yeah. So if you imagine like this is the person right here, and we're just gonna move left or right, up, or go up and down in this case. So either up or down. Okay, this is where they start. They might move here next, because randomly, and then they move, left or right. It's like, oh, they might move right again, and then they might move like, okay, left again, like this. Okay, and so the idea there is that it depends where they were previously, but it's random for every new step. Okay, versus a random, a white noise model, you're randomly going to be some value on that, on this range. Does that make sense? More or less. Andy, go ahead.
Can we think of it like playing chess?
Can you explain a little more?
So like a chess piece, you can move up, down, but then it won't be the same spot as previously.
Yeah, she's saying like next turn, like you're going to be in a different
Yeah.
spot. Yeah, you can think of it like that, kind of like a game, like you're moving along in the game and stuff like that. I think the reason why we call it a walk, right, it's because like you aren't just like getting a new spot every single time. Like you're not going to teleport all the way over there, right? But you might take enough random jumps to the left that you might end up over in that side of the room or something like that. Does that make sense? So I think it helps a little bit actually seeing what it looks like different from this. So let's kind of, okay, I'm going to skip over properties for a second. Let's see an example. So I'm just going to start with average 0, standard deviation of 10. And basically that just means that we have a normal distribution starting at 0, but standard deviation of 10, so we might go a little bit above, a little bit below, so either positive or negative, right? And if we run this, you can see here, that's a random walk. Okay, so you can see here, it basically, we started at 0, and it just happened to go negative, 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 right? But you can see this is still random, right? It just happened to go negative right here. And we do this a long enough time, right? We'll see this over and over and over again. Like we'll keep going progressively towards, not towards direction, but like if you're right here, negative 300, because you happen to like by chance always flip like heads and end up going like down to this point, right? Even if you flip tails next time, you're only gonna go up a little bit. You're not gonna suddenly teleport over across. Versus over here, you can see we started off like this really high value, but also we just jumped down, right? And that's because we don't care about where we were. We just say, what's the next value that's randomly? Where this one is like, we care about the next random value, but we start off at this point. Does that make sense? Like we're starting off this one point and move forward. So maybe if I do like another example, let's do another random one. I just don't want to ruin my time series. So let's call this, let's call DSE. There we go. So let's run that. So you can see here, if I run this now, you can see that in this case, we're going random, 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 right? We're just each of these little fluctuations. Maybe I'll just put like 10 points. And you can see here, we started here, right? In this case, we went like down like 15, and then we went up like, you know, looks like almost 10, right? Or a little over 10. And then we went up a little bit like 1, and then going up there, going there. And so basically your model is like each single point is going to be a randomly generated value, but you're still going to remember where you were previously. Versus a white noise model, you don't care where you were previously. You're just going to have the random value. Okay. Give me a thumbs up if that makes sense. Sideways, you're like, I don't understand. Thumbs down, like, lost. Okay. I see 2 brave souls going sideways. So I think, to me, I see Nadine kind of give like what could be a thumbs up, but like also like could be debatable sideways. Okay, good. So yeah, I'm assuming all of you guys are like, I don't know what's going on. So maybe it does help if I go through the code. So remember with white noise, right? All we did was generate a normal distribution, right? Didn't matter what the last point was, right? All that mattered, if I do time series, oops. All that mattered was it's just giving me a random number. Oh, that's because this is time series. But like, it would just give me a random number. It didn't matter what it was, right? It didn't care what the previous number is. For a white noise model, we say, okay, we're going to have a random number generated, but first start off what you were previously. So YT is the time series itself. So it's going to be the random walk. And then YT minus 1 says, look at the point previously, look at where you've been before, and then add in a random noise. Do you go to the left, go to the right, you know, by how much? And that is what this model is, and you just keep running that over and over again. And that's why, for example, these points seem very connected, right? Like they seem like, oh, they're moving along, right? They're walking essentially, versus over here, it's just like completely random, right? It's like each given point, you just teleport to a new spot. That makes sense? So I'm trying to get the walk in there. But so we implement this, the way this is done, and this is where like the code might be a little confusing, but it's super efficient in this way. We set the date evals, right? The epsilon is literally the white noise model. So you look at that right there, NP dot normal standard deviation endpoints. Okay, so this is literally the white noise model, right? And then we can see here, as we start off at 0, so we're starting off at 0 and say, all right, the first turn, okay, what did the white noise tell us? Well, white noise told us to go, you know, -10 or -3 or +3, whatever that random is. And then you move in that direction. So this Y0 plus, like you could think of it like the next set. The difference is that this cumsum, it makes a nice series so we don't have to like continuously like do a for loop. We could do a for loop like going over and over again, like saying, okay, like I'll just quickly write this because I think that you guys will understand this. So like for, this is not real code that's gonna work, right? For I, or let's say for step in white noise. So we have a whole bunch of white noise, completely random, right? Y equals 0. And then Y equals Y plus step. Okay, does that make sense? So we'll get a new step. So if I instead change it out to like, say 0, 10, -4, 5, right? Like that. Okay, every time we're going through, the first step is gonna be like, okay, the first one is gonna be at 0, the second one's also gonna be at 0, next one's gonna be at 10, the next one's gonna be at 6, and the next one's gonna be after that 11, right? Does that make sense? Like those are different points. Give me thumbs up if you guys follow me so far for this for loop. Okay, I think I see thumbs up. Okay, cool. So you can kind of see how this happens, right? So what this is equivalent to is saying, oh, that's Y equals Y like the first y, I'm going to call it y0, right? Plus y1, okay? The next y is going to be equal to, well, I should say this is just y0. The next one's going to be y0 plus y1, right? Next one after that is going to be y0 plus y1 plus y2. Does this make sense? Like the y2 is just this new step. So I should just call this like step. Does this make sense? I'm trying to make this as easy to read as possible. Okay. So basically y1, y2, and the next one's y3. What would y3 be? Someone tell me how I'd write this.
It would be basically like the initial y of 0 plus the first step of 0 plus the 10, or like the next step plus the -4.
Oh, you know what? You're right, Jessica. I realize I'm writing this wrong. This should be like a step. See, this is why I don't like doing things on the fly. This should be like step 0, step 1, right? Does that make sense to people? Okay, and this would be, I think that's what you're saying, Jessica, right? Plus the next step, and then plus the step after that.
Yeah, up to the -4.
Yeah, exactly. So that's kind of what's going on here. So one way to write this, instead of having it like go over and over like this, you can say, well, okay, all you have to do is just the cumulative sum. Well, the cumulative sum for the very first one is just going to be 0. The cumulative sum of this one is going to be 10. Next one's going to be 6, right? The next one's going to be 11, right? And then it's just plus, you know, so what this is going to look like. It's going to be plus 11, plus 6, plus 10, right? Does that make sense, people? So you're going to start off, the first one's going to be just a plus 10. That's what this is equal to. This right here is going to be plus 6. This one's going to be plus 11. And they just start off with a different point. So I can start off with 1 or 2. And that's what this MP cumsum is doing. Does that make sense? Okay, cool. All right. Maybe it helps. I'm trying to think of like ways to make this easier, because I know you guys are nodding, but I feel like it's like, is it really there? So let's see what he's talking about. I'll do epsilon. So you can see epsilon right here is these first points. Let's do for, I'm trying to think of how to do this real quick. Say for E, comma, this is gonna be cumsum in epsilon in the cumsum.
What does zip do? Because I know I've seen it before, but I haven't used it before.
Yeah, so zip basically, like if you look at NP epsilon, so for example, if I have like a list of like 1, 2, 3, 4, 5, and then I have a list of that's like 10, 20, 30, 40, 50, zip will basically put those together in a tuple. So I think that's actually really important, because who knows, like, did anyone know that about zip? Like how to use zip? Give me a thumbs up. Okay, good. So I just want to make sure you guys know. So 1, 2, 3, and then 10, 20, 30. Oh, well, I forgot. It's going to give me a generator. So we go to like, I'm going to use a list comprehension. So it'll be like, I'm trying to think of this, A comma B for A, B in zip.
I think I get what you're saying now. So it'd be a tuple of like 110, then like 220, then like 330. Is that what you're saying? Okay, cool.
That's right. I think I had to do this anyway. If not, there we go. So there you go. So that's what's going to happen. It's going to pair up each part, right? So that's what this MP cumsum is. And you can see the first one's going to be minus 14, but the second one, this epsilon, right, it's only 5. So the cumsum is going to be minus 14 plus 5.957, right? And you can see that's going to be minus 9. And then the next one's going to be adding 5 again to it. So it's going to add up this one, and this one together, and it gives us minus 3. So that's what the cumsum is going to do. It's just basically saying how far it goes off. And that way you can get this really quick model over here. What I was trying to get at basically was trying to show you like how it depends on like where you were previously. Another example of this is like a random, does anyone ever understand like random walk now? Like, is that helpful? I think if you think of it like, I honestly think if you think of it like a drunk person, like saying like, oh, they can go left or right for every step, like where will they go in the room? That's kind of what's going on here. They're just randomly going left or right. It just happens to be down. If I run this again, it won't be the same thing. You can see here, like this seems a little more random, I think, right? It's like they happen to be taking a lot of steps to the left, like maybe they're like kind of like tripping over to the left and they kind of gain their balance a little bit, tripping off to the left right here and so forth, right? So a variation of this is a random walk with a drift. And with this drift right here, basically it just means like there's this added constant, C, and that drift is kind of like equivalent to like the floor is slightly slanted, right? So every time they take a step left or right, they take an extra step left, right? So like maybe it's like kind of like slanted off like this side. So they can go left or right and they might take a step right, but then they also take a step left because they're always going to be pushed over to the side. You can also think of it like maybe there's a little of a breeze. I don't know, like there's a breeze kind of pushing them like with some force. And so they're always going to end up taking a step to the left every single time, right? Because there's kind of this extra force pushing them. So in this case, you can see here, I think I put both of them on down here. Yeah. I have the original random walk right here. In a random walk with a drift, it's just going to show you the same random walk, but it's going to drift upwards. So you can model this basically just saying, oh, let me just do a random walk, which is this guy right here, and then just adding the constant C. In this case, just adding C every single time going through. Okay. Cool. All right, those are the two basic models. With those two basic models though, and I know we're over time, so I think I might hold off on this. We might take some time next time. With those two models, we can actually do autoregressive models, basically by using the fact that we know what white noise is and the fact that we can kind of like say, oh, what's the previous point from before? We can basically use that to create an AR model, autoregressive, or a moving average model. And basically those are both the same thing, the same idea of like a random walk or a random walk with a drift. But it's a little more complicated because we get to like multiply by like the previous point and stuff like this, which is a little complicated, but it's not that bad actually. It's just kind of like iterating over and over again. And it turns out, again, they turn out to be pretty good. And you can make these models from here. Okay. All right. Yeah, should we stop here then? I think that we kind of been going for a while and I don't want to like break everyone's brain. Like a good hour 15, I think it's a good amount of time, right? Okay. All right, so I'll stop it here. I'll tell you what, next time for study group, right, we'll talk about ARMA just because I figured people have questions on this, right, how this works. And then, ooh, does anyone remember what the next section 39 is? Is that, oh, natural language. So next, is anyone on section 39 by chance? Okay, good. So I think what I might do, I'm trying to think of this through. Let me just look at this real quick because I want to make sure. Yes, we're going to skip section 39 for right now. And the reason why is because you will get a lot more out of section 39 if you know neural networks. Okay, so we're actually going to go skip section 39, go into section 40. So we'll finish up time series section 38 next time. Then we'll start into neural network section 40, and we'll kind of do these together. And then we'll go back into section natural language processing. Sound good to you guys? Cool.
Would you recommend we do that as well on LearnCo? Like, should we skip to?
Yeah, I think I'm pretty sure. I'm just making sure. There's nothing in here like section 39 where like, oh, if you didn't do section 39, you're not going to understand section 40. These are pretty independent from each other in a sense. It's actually funny. I think this is going to be more confusing for, where is it, bird vectorization. And I want to talk about embeddings, which are pretty modern. You guys will hear about word embeddings if you talk about NLP, but those things generally rely on the fact that you have neural networks already. So that's why I kind of want to skip this so we can talk about embeddings in the context of neural networks. Okay. Cool, makes sense, people? All right, awesome. Okay, everyone, well, I'll stop sharing here. Good to see you all. I think I have maybe a one-on-one with at least one person. I can't remember who it is on my calendar for tomorrow. It's Andy, sweet. But if you guys haven't had one-on-ones already, definitely message me out. I'll get the link out. Like I think Jessica asked last time, having that link for like just signing up. I'll get that situated by the end of tomorrow. So that way, at least over the weekend, you guys can sign up for one-on-ones, or you can just message me. That's going to be the most direct way for right now. But yeah, I'll see you guys all around then. It's actually next week. All right,
See you next week. Thank you. Bye, guys.